All right, I think we can get started. Thanks everybody for joining for our Science in the News seminar series. My name is Jacqueline and I'll be moderating today's talk. And we are going to have a talk today from Michael Foley, who is a fourth year PhD student in astrophysics at Harvard University. He's studying star formation and turbulence, and recently has become very interested in the possibilities offered by 3D dust mapping. Outside of research, he enjoys singing, volleyball, and searching for free food. And in today's talk, he will tell us about how 3D dust mapping can help us map out our galaxy and understand the story of how our sun came to be. So take it away, Michael. Looking forward to hearing your talk.
Awesome. Thanks a lot, Jacqueline. Like Jacqueline mentioned, my name is Michael Foley. I'm a graduate student here at Harvard. And as she mentioned, I've recently become interested in the possibilities offered by 3D dust mapping. And I'll get into exactly what that means and why it's so exciting for understanding our galaxy. I first want to clarify that this first image I'm showing is just a cartoon of a galaxy, but it does have a dot "you are here," and it asks an important question, why? And by the end of the talk, I hope to provide a little bit of context for why our sun falls in its particular neighborhood of our Milky Way galaxy and what we can learn through 3D dust mapping about that neighborhood. So this talk is going to be split into 3 parts. We're going to first ask what components make up a galaxy. After that, we can ask, how can we know where these components are in space? And this is where I'll get into the 3D dust mapping technique and what it can tell us in the third part about where our sun resides. And so after each part, we'll have a short break. We'll reconvene and we'll sort of think about what we've learned in each one of those parts. And then at the conclusion of all 3, we'll come together and see what 3D dust mapping really is able to tell us. So first, I want to talk about what actually makes up a galaxy. So I'm showing on the right here a simulation of a galaxy that should be roughly similar to the Milky Way in mass and composition and stuff. And I want you to just take a look at this. Notice whatever you can, whatever comes out as an interesting feature to you. And type it in the chat, either on YouTube or on Zoom, or if you feel so compelled. This simulation was made with the latest knowledge of how galaxies look, but it's important to go to simulations for some of our physical understanding, and I'll refer to simulations throughout this talk, because since we fall right in the center of our Milky Way and it covers such vast distances, it's hard for us to get an understanding of what the 3D structure of our Milky Way looks like, since we're inside it. So using simulations like this, we can get a bit better understanding. But I'll talk about later in the talk how we can start comparing simulations and new 3D observables to gain even more insight. And so I see at least one message mentioning the dark and light spots in the simulation, which is great. And those highlight 2 really important components in a galaxy. So this right here on the right is just a screen grab of part of the simulation. And I've highlighted in particular some dark spots, which you can see they're sort of blackish, brownish throughout. And some of the bright spots you see like right at the center of the image and at the other points of the arrows. And the dark spots in the simulation correspond to what we call gas and dust. And I'll get a little bit more into what those are in the next slide or 2. But the bright spots correspond to stars. And so the 3 major components of a galaxy are gas, dust, and stars. And in this talk, I'll be talking about how stars can help us learn the 3D structure of gas and dust, and what it means for our understanding of star formation and how our sun came to fall where it is in our Milky Way galaxy. And so for a little bit of context, so we have our dark spots and our bright spots in our simulation. We can also kind of observe these in our Milky Way on the sky. So if we go back to the simulation on the left, we kind of zoom in to roughly where our sun would fall if that simulation were our Milky Way galaxy, and then we tilt it to the side, you'll see something that looks roughly similar to what you might see if you go out to a dark sky spot somewhere where there's very little light pollution and look up in the sky. In particular, I'm looking at like the dark lanes as shown in both the observed image and in the simulated image. So you see these sort of lanes of dark, dusty material, and then you also see some stars popping out the sides. So like over here. Back in ancient times when light pollution was just a non-issue, people actually were able to see the dark spots so well that they came up with constellations for these dark lanes. So the same way we have constellations made out of the stars, like Orion or Perseus or Taurus, people actually came up with constellations using the dark and dusty lanes in the Milky Way, which I think is pretty cool. And so this sort of galactic context we can even see from our backyard, but to really understand things in 3D beyond this sort of 2D image, we need to go to more sophisticated techniques. So to understand what's really going on in a galaxy, it's crucial to understand the interstellar medium. And what is the interstellar medium? Well, we can break it down into its three component parts: inter, stellar, and medium. Inter means between, stellar just means stars, and medium just means stuff for our astronomical context. And so the interstellar medium means the stuff between stars. So generally the stuff that's hard for us to see on Earth, all the gas and dust and stuff that's floating around in a galaxy that isn't emitting light as strongly as stars. And the interstellar medium falls kind of far outside our solar system. So for context, our solar system goes out to about roughly 100 AU, and 1 AU is the distance from the sun to the Earth. So about 100 times the distance from the sun to the Earth marks the boundary between our solar system and what we would start calling interstellar space. The Voyager spacecraft, which launched back in the 70s, have just now reached what we would call interstellar space. So we have actually created spacecraft that has reached this interstellar medium, but it's just barely getting there. And the true interstellar medium falls closer to 1,000 to 100,000 times the distance from the Earth to the sun. And you can see over on the right here, Alpha Centauri. That's the closest star to us, and all this sort of gas and nebulous material in between, all this fun stuff right here. This is all what we'd call the interstellar medium because it falls in between our sun and other stars. So with that in mind, we can start studying the gas and dust that fills the space between stars if we're willing to go to different wavelengths. So on the left here, I'm showing a picture of the Orion constellation. If you were just standing out in your backyard and looked up in the winter in the northern hemisphere, this is invisible light. If we go to infrared wavelengths on the right, so a longer wavelength of light, we can start to see some of what we'd call the interstellar medium. And this is composed of gas, which is very small molecules. It's typically only composed of a few atoms, but gas is responsible for actually making stars. So even though it's very small, it comes in large quantities, and it serves as really the material we need to form new stars. And then dust, which is much larger than gas. It's typically composed of thousands to millions of atoms, but it obscures light from the stars. So our two components of the interstellar medium, gas and dust, serve two different roles generally. Gas, it primarily is making the stars, and dust is primarily obscuring light. So we can use the fact that dust obscures light in our 3D dust mapping technique, and I'll get to that in section 2. Oh, and then just to highlight this sort of idea, what has appeared in the bottom of your screen isn't a smudge. It's just sort of a conceptual of what happens with dust, which will stand in between some light source, and us. You'll see that come back in section 2. But what does the gas look like? So we can actually see the gas, even though it's much smaller atoms, and the dust does a lot of the obscuration of light. Gravity brings together the gas, forming clumps like we see on the left. This is the famous pillars of creation. And these clumps are what we call molecular clouds. You don't need to worry too much about the terminology or what's behind the meaning of molecular cloud. But keep in mind that molecular cloud means where stars are born. They're the birthplaces for new stars. And we can use dust as a tracer for these molecular clouds. To show what I mean, if we look at an image of another galaxy, so this is another one far outside our Milky Way, we can identify regions where light is obscured. These are sort of darker, dusty regions in the image. As you can see, sort of pointed to by the arrows. And then if we consider those in the context of molecular gas, shown on the right here. So the molecular gas on the right is highlighted in red. So if we go and then look for where the molecular gas falls, it falls exactly kind of where the dust is. So through observations of other galaxies, through observations of our own galaxies, we can find that the gas that makes stars, this molecular gas, these molecular clouds, are traced well by the dust. So the dust that's obscuring the light serves as a nice proxy for us where stars are forming. So the darker regions on the left correspond to the red regions on the right, meaning that dust and gas serve as nice tracers of each other. Now, these molecular clouds that are forming stars, they don't persist very long in terms of galactic timescales. They're quite transient, actually. So on the right, I'm showing a galaxy simulation that I'm going to blow up to. So don't worry, I know it's kind of small on the screen right now, but every cross shown in that simulation is tracking an individual molecular cloud, an individual sort of large clump of gas that's going to form new stars. Those crosses are popping in and out of existence on the timescales of a few to maybe a couple tens of millions of years. So that sounds like a very long time, but that pales in comparison to galactic timescales. So for context, the dinosaurs were still alive 60, 70 million years ago. Many generations of molecular clouds have passed in and out of existence since the dinosaurs even lived on Earth. So the birthplaces of stars pop quickly in and out of existence. They'll form stars, and then once stars are formed, they kind of disperse, and I'll get into why exactly that is. But the reason this is important is because if we are tracing sort of this molecular gas with our 3D dust mapping technique, it's important to note that these molecular clouds are changing on rapid timescales. So what we observe now is not what has always been in the galaxy. And so to highlight kind of what I mean, if we zoom in on like the top part of this simulation, you can see it's kind of like fireworks. These crosses are popping in and out of existence super fast on scales of a couple million years. And so to understand our solar neighborhood, it's first important to understand what makes up a galaxy. So to briefly summarize what we've covered shortly in this first section, galaxies are made up of gas, dust, and stars. Gas forms new stars. Dust obscures light from those stars, and dust and gas tend to follow each other. And molecular clouds are large clumps of gas and dust that form stars. So we have gas and dust together in molecular clouds, they're forming stars. Those will be the tools we can use to start making use of our 3D dust mapping technique that I'll talk about in section 2. And molecular clouds live very short lifetimes, from a few to tens of millions of years, which is quite short on galactic timescales. So when we talk about our 3D dust mapping, we're only mapping things that currently exist, and we're not learning too much about the large-scale history of our galaxy, but that doesn't mean we can't tell a very important story for the history of our sun. So up next, we'll talk about how we know where these components fall relative to our sun. And then, Jacqueline, or do we take a short break after each section and take some questions, or?
Yeah, are there any questions from the audience? All right. Well, if not, perhaps we can.
Oh, sorry. I can't
Oh,
hear
sorry. We can take a break for a few minutes. Maybe let's resume in 5 minutes, maybe like 6:55.
Sounds great.
Thanks.
Great question. So we think that the compositions are slightly different. So the gas are mainly sort of few atom molecules, and the dust are much larger molecules. The gas is primarily hydrogen. So it's either a single atom of hydrogen or the molecular form of hydrogen. So two hydrogen atoms together. And so when we talk about molecular clouds, those are primarily composed of molecular hydrogen, the sort of two hydrogen atoms together. And then the dust is generally much larger, but its backbones often are carbon or silicates. So it's more complex material that is generally made up of elements that have been produced in previous generations of stars. So as stars form and live their lives, they'll fuse heavier and heavier elements in their core, and eventually then they'll return that to the interstellar medium. So gas is the simple molecules. Dust is stuff that's been reprocessed by stars, basically returned to the interstellar medium. And now it's like these big molecules that are obscuring light from stars. So you can almost think of it as sort of like the component of the interstellar medium that's in its teenage phase. It's upset with its parent stars, and so it's kind of living out its own life now.
I have one question. You mentioned that molecular clouds have relatively short lifetimes. Do we know like how often they make new stars, or like will one molecular cloud make multiple stars during its lifetime?
Yeah, that's a great question. So we think roughly it's still kind of an open question, but we think about 1% of the mass of a molecular cloud will make it into stars. Most of these molecular clouds are on the order of 1,000 to 100,000 solar masses. So a molecular cloud generally might make, taking that an average star is about the mass of our sun, an average molecular cloud might make tens to thousands of stars. And that's actually a great segue into part 3 of this talk, where we will learn a little bit more about star formation and how it interplays with 3D depth mapping.
Great. We have one more question in the chats. They're asking if it obscures gas because it compromises larger molecules, or because the contents are less transparent.
Great question. Both. So the molecules are more susceptible to absorbing light, and they're also just larger. And because of their locations to stars, they tend to you'll find dust in dense regions, and so when you have a lot of dust close together, and they're larger molecules, and they're less transparent. It's sort of like a holy trifecta for blocking light.
Very cool. Well, I think if you're ready, we can go on to part 2.
Yeah, sounds good. All right, so we've talked about what galaxies are made up of, gas, dust, and stars, and how those relate to molecular clouds. So next, we're going to be talking about how we actually know where these components are in our own galaxy in 3D. So one particular satellite has made sort of revolutionary transformations in this field, and that is Gaia. It's a satellite that was put into space by the European Space Agency, and it can measure the distances and motions of billions of stars quite accurately. So for most of human history, when we look up at the night sky, we'll see things in 2 dimensions, basically up and down, and then left and right. Gaia is transformative for astronomy because it adds in a 3rd dimension, the distance along the line of sight. So if we have 3D positions for these stars, we can learn a lot more about the structure of our galaxy. And it tells us how these stars are moving over time. So we can start constructing a little bit of an evolutionary history of the stars in our galaxy. And they're putting out a new data release in June, which the entire astronomical community is very excited about. So look for a lot of new and exciting science coming this summer with this new data release from Gaia. So like I said, Gaia records both the distances to stars and their motion on the sky. So on the right, I'm showing a visualization made by the Gaia team of what it would look like if we could peer forward in time millions of years. So all the stars we see on the sky right now are going to move quite substantially over the course of the next couple million years, which means things like the constellations you see won't exist from our vantage point on Earth in a couple million years. All those stars are going to, sorry, there was some sound associated with that video. All the stars associated with those constellations are going to move and tessellate. And so the constellations will look very differently from our vantage point on Earth in the next couple million years. So to connect the innovations from Gaia to 3D dust mapping, we have to make a few sort of modeling assumptions. By observing all of these stars from Gaia and using and making record of their 3D positions, we can use a concept known as reddening to locate where the dust is falling in 3D space. So to illustrate this, I've made a little schematic on the right-hand side where our research group has, and it's going to show exactly what happens when you're looking at a bunch of different stars on the sky with dust in between. So let's imagine that you're just observing one yellow little star up here, but you have some dust in between your telescope and the star. That's going to redden some of the light we get from the star. The same way that when we look at the sun, when it's close to sunset, you're looking through more of the atmosphere and it reddens the light from the sun. So a sunset is redder colors than you would see during the day. When you're looking through a lot of this dusty material, it's going to redden the light from the stars. If we have a lot of stars, like we do from Gaia, we then can, sorry, there's a little motor outside my window. We can then keep track of how much reddening is applied to each star. And with a record of enough stars, we can then make a 3D map of exactly where the dust is falling and how much it's reddening each one of these stars. So with billions and billions of stars, like Gaia provides, this technique of reddening can tell us exactly where the dust is falling because it is reddening the light we observe from the stars. And so this has been revolutionary for our understanding of astronomy. So on the left, I'm showing the sort of first generation that came out of 3D dust maps, and it's going to be a video where we can sort of fly around and see a little bit of the 3D structure of our galaxy, which is absolutely beautiful. And I'll be explaining exactly what's going on in this video as we go back. So black in this video is dust. This is stuff that's obscured by, or that obscures starlight. And this was mapped out using the technique I mentioned in the last slide. You can figure out where the dust falls relative to where we know all the stars are and the reddening that's occurring. Blue text here indicates some famous star-forming regions, some famous molecular clouds that have been very well studied in astronomy. And you might notice some of the names here from mythology, like Taurus and Perseus. A lot of these are associated with constellations in the sky. So people first discovered constellations in the sky. They later found out that these molecular clouds happen to sit pretty close to the constellations, if not within them. And then they named the molecular clouds after the constellations, which derived their names from mythology. And so I'm gonna go through this video again, and I wanna highlight one particular feature. So you can see a lot of cool structure. In particular, between Taurus and Perseus, you can see a little bit of a void that forms. We'll talk a bit more about this later. But on the plane of the sky, it appears like Perseus and Taurus are connected. So if you were just looking up at the night sky, you looked in infrared wavelengths, you'd be like, okay, this might be one cloud. But with 3D dust mapping, we can start to untangle the mystery of what's really going on here. And it appears that there is quite a space of separation. You can see right here, a white space forms a void between them. There's quite a separation between Taurus and Perseus. So this is an exciting thing that our research group discovered a couple of years ago, and I'll talk more about that discovery later on. So 3D dust mapping can start to help us revolutionize our understanding of the night sky, going from 2D to 3D. And so this is a top-down view of our galaxy in 3D. So there's a lot going on here, so I'll step through this too. So the panel on the left is a large scale top-down view. So the entire plot shows roughly 5 kiloparsecs on each side. A kiloparsec is 1,000 parsecs, and 1 parsec is about 3 light years. So we're talking about 15,000 light years across the left panel. This is a huge distance, and we can start mapping out incredible components of our galaxy now in 3D. It doesn't have the greatest resolution yet, but I'll get to the newest advances that have come out in the last couple of years that really enable us to do better. And then in the middle panels are just zoom-ins of particularly interesting regions. The bottom panel, which is then blown up farther on the right, shows a zoom-in of the region around our sun, which is shown in yellow. This is our solar neighborhood in the top-down view, which is quite remarkable to think of. We'll never be able to send a probe that gets a picture of the top-down view of our galaxy. It's just too far away to get a camera up and out of our galaxy. But we can start mapping out the 3D structure and now get a top-down view using 3D dust mapping. And so you might notice some of these names again: Perseus, Taurus, Orion, Chameleon. I'll talk more about all of those later, but we can now locate them in 3D space. And you might notice too that there's some interesting structures within this 3D space. First off, you might notice that there's a large white section in the bottom right corner. That is not physical. That is because the telescope that got a lot of this data was in the northern hemisphere, and so it couldn't observe all of the stars in the southern hemisphere. And so it missed out on a chunk of the sky. So in reality, this is filled in. This is a full sort of top-down view. But you might also notice that there's a long, straight, skinny thing of blue points here, where every blue point indicates a single sort of molecular cloud, or a data point within a molecular cloud. This is a structure that our research group discovered about 2 years ago. So this is still kind of cutting-edge research. That we've called the Radcliff Wave. It's about 3 kiloparsecs in length, meaning it's close to about 10,000 light years in length, and it falls right next to our sun. So if we look in the zoom-in view, it's right there. Our sun falls right next to this giant, long, straight structure And it's kind of unclear how it got there, how it formed, and what it implies about our galactic evolution. So this is sort of an active area of research that has just been revealed by 3D dust mapping, where on the right I've just sort of blown up that red selection along the zoomed in view. So this was only discovered back in 2020, like I said. So 3D dust mapping really is just kind of in its infancy, but it's already revealing really incredible structures and knowledge about our local interstellar medium. And this Radcliff Wave includes many of the nearby molecular clouds and stellar nurseries, or places where new stars are being born. And if you'd like to play around with this data yourself, we made many interactive figures that are available online. They'll be linked in the handout for this talk, but you can click on them. You can rotate everything, you can zoom in, you can see the data yourself, because with everything in 3D, we can actually interact with it now, which is really exciting. But that wasn't enough. We want to go even higher resolution. So if you're looking on the left, you might notice that it's just kind of blobby. There's a lot of just large black blobs. It's not super high resolution. It's kind of like if you looked back at a Nintendo 64 versus, video games nowadays. So we've been able to go to even higher resolution dust maps thanks to Gaia and its treasure trove of stars. So on the right, I'm showing the high resolution version of the zoom in near our sun. We've been able to make incredible advances, going from a couple 100 light year resolution down now to almost single light year resolution, where our sun is still in the center here. And then you can kind of even see the similarities between the two. So once this stops, you'll see on the left, here's this sort of long straight thing. That was the Radcliff Wave that runs through here. And then there's a big void right around our sun. We'll get to that a bit later, but on the right, there's another long straight thing. You can see that over here. So high resolution mapping takes us far beyond what we were able to do, even just only a couple of years ago. And this void around our sun has turned out to be an incredibly interesting thing, and that'll make up a lot of part 3 of this talk. But with this 3D dust mapping, we also can just observe the 3D structure of molecular clouds for the first time ever. So on the left here is what you would see if you looked up at a molecular cloud just on the sky. It looks kind of disconnected, but this is what people have used for all of astronomy and human history. On the right is a plot that came out by someone in our research group, Catherine Zucker, this previous year. And it's part of an interactive figure where you can actually rotate and view and zoom in on the molecular cloud in 3D, which is the first time we've been able to do that. And it'll be very exciting to study what that means for star formation. And we've been able to do this for all of the local star forming clouds. So remember Perseus and Taurus. We now have 3D views of those and some of the other major ones, such as the Orion clouds and Ophiuchus and Cepheus, which we're very excited about. And in particular, Perseus and Taurus serve as kind of an interesting case study because they looked like they were connected in 2D on the sky. In 3D, we can really show that that's not the case, which is what I'll get to in the sort of first point for our next chapter. But so to summarize, how can we know where these components are in space? Well, Gaia has been the major factor. It allows us to understand where stars are and how they move. And these maps of stars allow us to map out the dust in 3D by using this technique of reddening, looking at stars, seeing how much the light reddens, and with enough stars, we can then create a nice statistical map of all the dust. And we can use this to map out many molecular clouds near our sun in 3D and create interactive figures that anyone can play around with. And so up next, I'll talk a little bit about what this means for our physical understanding of where our sun resides and what it means for the story about, how we got here. And with that, I'd be happy to take any questions about section 2 or go to a short break.
have any questions about this part? Maybe I can start with one. How does this dust mapping technique have higher or lower resolution depending on how far away the dust is from Earth? So is it harder to map things that are further away?
That's an excellent question. Yes, it is. So if you'll notice here, we were able to go out very far. This is a much larger dust map on the left, but in much lower resolution. So this goes out, for the 15,000 light years. Our high resolution map only extends as far as this cube does, as far as this zoomed in view goes. So we were only able to get high resolution for this very zoomed in view. Our dream is to do high resolution for much farther distances, but that requires more stars to be more confident in the dust. So we're waiting on the new data release from Gaia, and hopefully new telescopes.
Very cool. We have one question in the chat. Is there a reason that the two dust clouds, the Radcliff Wave and other, are parallel to each other, those straight lines?
That's an excellent question. And that is one we do not know the answer. We have many theories for it. Our group meeting has been devoted to that question actually for about the last year. And so if you have any ideas, we'd love to hear them because we are actively investigating that too. And hopefully within the next few years, we'll have a better answer. But it's quite interesting that you have two long straight things right next to each other.
How big, like how does the size of the Radcliffe Wave compare to like the full size of the Milky Way, for example?
So it's actually a fair amount. So the Radcliffe Wave we think is about 3 kiloparsecs in length. The Milky Way is on the order of tens of kiloparsecs. So the Radcliffe Wave, just in length, occupies almost about a tenth of the size of the Milky Way, depending on how you measure it. So we think it forms part of the local arm of a spiral galaxy. So when you see these beautiful pictures that look kind of like whirlpools, we think the Radcliffe Wave forms a large part of one of those swoopy arms.
We have another question in the chat asking what's the work principle of Gaia?
I'm sorry, what was that?
Um, they're asking what the work principle is of Gaia. Maybe they're curious about like how often you can get data from them or things like this.
So the beautiful thing is it's a robotic telescope operating in space, so it can take data around the clock. So it releases new data roughly, once every year or two. So this data that we've been working with that produced this new high resolution map, that was released a couple of years ago. So this new data release coming out in June is going to be the first time that we've seen new data in a little bit. And then hopefully Gaia will continue releasing data on that cycle for many decades to come because it's doing awesome work.
And we have another question from James on YouTube asking if there's things like the Radcliffe Wave in other galaxies.
That's another great question. We're actively looking. We do observe things that look kind of like the Radcliffe Wave in simulations, and just from the best data we have of some other nearby galaxies, we do observe things that look like the Radcliffe Wave, at least in their extent and their general width. The problem is we can't get 3D information for other galaxies the same way we can get 3D information here. So we have things that look long and skinny, like the Radcliffe Wave in other galaxies, but we can't exactly see in 3D. So those things could just be projection effects along our line of sight that add up to look like a long, skinny thing. So we're trying to investigate that too.
Great. Thanks so much for answering all of those. I think we can take another few minute break. Maybe let's resume at 7:20 and we'll go into part 3.
Sounds great. Turbulence. And so turbulence has the exact same meaning in space that it does on Earth. It's just sort of chaotic motions of gas. So when you're flying, it's the chaotic motions of gas that make the flight so exciting. If you hear a pilot talk about turbulence, it's because the atmosphere is moving in a very chaotic fashion that disturbs the flight path of the airplane. And this turbulence, as you're seeing on the right, it'll evolve over a couple million years. It can create other sort of gas clumps that will then collapse due to gravity on small scales. So 3D mapping through 3D dust mapping can help us understand where these density enhancements occur. So where you might get these little clumps within a molecular cloud that end up forming stars. And then the third piece of physics that is really important for star formation is magnetic fields. So magnetic fields play a role in directing particle motions. On Earth, they're the reason we're not dead. If we didn't have magnetic fields around Earth, we would just be completely fried by radiation from the sun. But the magnetic fields on Earth do protect us from a lot of the solar radiation and redirect the charged particles from the sun away from us. And they're responsible for the aurora in both the northern and southern hemisphere. So if you've ever seen like the pictures of those beautiful lights, that's because charged particles from the sun are funneled along magnetic field lines to the top and bottom of Earth, the north and south sort of magnetic poles, and those form those incredible light displays, which are really just charged particles from the sun interacting with our atmosphere. So we know the magnetic field structure around Earth fairly well because we can send out satellites to detect it. We can use a lot of different probes to get that structure, but we can't do that for the interstellar medium. So getting the 3D structure of magnetic fields in the interstellar medium is very hard. It's very hard to observe. And their role in star formation, consequently, is under active investigation. We can simulate them, but it's really hard to confirm those simulations with observables. And if you can't confirm whatever you're simulating on your computer with real observations, then you're just sort of playing around in the sandbox without really any scientific confirmation. But our 3D dust mapping can help us start understanding where things are happening in 3D, and potentially too, the 3D distribution of magnetic field lines. So dust mapping can really help us understand all three components of star formation: gravity and turbulence, in the creation of those sort of clumps of gas. We can understand where those are now in 3D. And then by understanding where those are in 3D, we can get more information about the magnetic fields in 3D. And so taking it all together, we have these three major components in a molecular cloud: gravity, which induces collapse of a molecular cloud and forms stars, and then turbulence and magnetic fields, which we believe mostly work against collapse, work to prevent the formation of new stars, but it's an ongoing debate in the field. And so all three definitely do play a role in regulating star formation, but 3D mapping will help us understand exactly what those roles are. And so the final piece of the physics puzzle that I want to introduce before we get into like the example I talked about for Perseus and Taurus and some more exciting examples from our local solar neighborhood are supernovae. So supernovae are one of the main components of stellar feedback, which is just an umbrella term for all the ways that stars feed energy and momentum back into their surroundings over time. Or in other words, the way that stars affect their surroundings throughout their lives and in their deaths. So supernovae are massive explosions at the end of a star's life, and they play a large role in affecting the interstellar medium. And we believe our solar neighborhood has had a lot of them. And with 3D dust mapping, remember that void I talked about before between the long straight things? We think that that was caused by a whole lot of supernovae, and we can actually tell the story for how we think that happened. So to highlight what I mean in a simulation, on the right, I'm showing again the evolution of a molecular cloud. Now all the stars are just shown by these colored dots. And at the end, a supernova goes off and blows apart the molecular cloud. So you'll notice that this happened at around 8.5 million years. We think that molecular clouds are so transient, they fade in and out of existence so easily because of things like supernovae. Once you form enough stars, one of them is going to explode and blow apart all of the gas and dust. So you might notice that this creates sort of what we call a shell. So if we look at the edges here, there's still gas and dust, but it's just in a big sort of circular cavity. We can now observe these circular cavities in 3D. And I'll show you an example with Perseus and Taurus. So this is a group, a video our research group made about the discovery. I'll mute the narrator and I'll sort of talk a little bit about what you're seeing. So what we want to highlight in this video is exactly what was seen in 2D, so what was known before 3D dust mapping, and what we think 3D dust mapping can tell us. So this is an artist's idea of what the Milky Way might look like. And we can zoom in to where we believe the sun would fall in this galaxy. And you can see here a lot of the famous constellations and the stars in 3D. We know the 3D positions of the stars now thanks to Gaia. And this view right here is the 2D view on the sky, what ancient people have seen. So there's the constellations of Taurus and Perseus. You can't see any of the molecular clouds yet. But if we turn on a different wavelength of light, the infrared wavelength I talked about before, you can then see Perseus highlighted in red and Taurus highlighted in blue. People thought these were connected for about a century because on the sky in 2D, they certainly look like it. But thanks to 3D dust mapping, we understand that this sort of idea of forced perspective, where you have things lined up along the line of sight, like that hand in a telescope, can create illusions. So even though that Perseus and Taurus look like they touch on the plane of the sky, Gaia has allowed us to map them out in 3D and discover that there really is a large spherical cavity between them. So you'll see right there that there's a large distance of separation, and we can overplot a sphere. And if we put on a lot of the other gas and dust in the region, we find that it fits pretty nicely. So Perseus and Taurus really appear to lie on the edge of a sphere instead of connected along the plane of the sky, like people had thought for a long time. So what we think happened to create this is a supernova went off a couple million years ago. It formed this large shell of gas and dust. And then on the shell, that is where we find Perseus and Taurus. So the supernova swept up material, and then out of this swept up material, we formed the molecular clouds. And they just compose a few of the molecular clouds in our local vicinity. So we're actively searching for any other bubbles that might have created some of these other molecular clouds from supernova. So this is just one case study about the effects of 3D dust mapping and how it helps connect physics to some of these regions that have only been studied in 2D for quite some time. And we've been able to make really cool visualizations given that we now have 3D information. So we can rotate this plot in 3D. It's fully interactive, and I'll put a link to this plot in the handout if you'd like to play around with it yourself. But in addition to just playing around with it on your computer, you can also download an app and visualize this plot in augmented reality, if you'd like. So you could walk around it in your living room and see Perseus and Taurus in their 3D distribution, thanks to this 3D data. This is the first augmented reality figure ever published in astronomy, which we did last year. And we hope that it heralds a sort of new age where you can take a lot of these astronomical data sets and start playing around with them in virtual reality or augmented reality, sort of like a video game in your own living room. So if we go back to our high resolution dust map for our entire interstellar neighborhood in 3D, we can start plotting out all of these 3D structures we've talked about. So these colored dots correspond to all those 3D molecular clouds that we were able to map out. The yellow cross at the center corresponds to our sun. And then this large shell between Perseus and Taurus is going to appear in a second. But we can see that the sun falls in the middle of quite a large void. There's nothing really around our sun. There's those two large straight things, but then a big void around the sun. And there you can see the shell that forms between Perseus and Taurus in 3D. So we think that that was created by a supernova. There's the Radcliff Wave in red. It goes sort of through that long straight line of dust over there. And now we can finally turn on the local bubble. So the local bubble is a large void that astronomers have thought existed around our sun for quite some time. They knew that there was not much material there. They knew that our sun was sort of in this hot region of gas that corresponded with a potential bubble produced by supernovae, but this is the first time we've been able to see it all in a 3D context. So someone else, another research group, was able to map the local bubble in 3D, and then by placing it in our 3D map here, we can see that it fits exquisitely well with our knowledge now of molecular clouds and all the other shells. So this is just the start of the structures we're starting to look at in 3D here. But to summarize everything in this plot, we can plot 3D positions and motions of stars. So some of these small little arrows, they're a little hard to see, I'm guessing, but over here we can plot clusters of stars and how they're moving. And we can plot 3D positions of molecular clouds measured by dust. And then we can start taking our simulations and implementing physical models for stellar feedback, along with all this other information. So that means that even though we're only observing things at one moment in time, thanks to our simulations, we can construct physical models for what might have happened in the past to get us to where we are right now. So we map things out in 3D, but we can add in a fourth dimension of time here. So what's being shown on the right is what we think happened to create the local bubble over time. So starting 15 million years ago, this bubble started expanding. And it reached this present configuration after a lot of evolution. So there's a lot kind of going on in this figure, so I'll quickly step through exactly what's going on. The sun here is shown as the yellow X, and the sun's actually moving relative to everything. The sun has not remained stationary for all of its life. So the sun has only now moved into its current position relative to all of this other material. The other colored dots correspond to other clusters of stars that are moving, and you can see that over time they expand with this bubble model. And then the purple corresponds to our physical model for how we think this bubble grew over the last 15 million years before it got to its current state. So you'll notice it goes from just a sphere into something that looks very non-spherical. This is because this is only sort of a simple physical model, but it grows at roughly the same rate. And we think that this bubble grew by repeated supernovae. So thanks to all of this mapping, we believe what really happened in our local solar neighborhood was that starting 15 million years ago, supernovae started going off. And over the past 15 million years, roughly 15 supernovae had to go off to produce this current void that we call the local bubble. And our sun moved into this void about 5 million years ago. The fascinating thing is that if our sun moved into this void, so right over here, around 5 million years ago, we would expect that on Earth, we might see evidence of some sort of supernovae, since the sun is moving into a bubble that was caused by supernovae. If we go back to the geological record and look about 5 million years ago, there is evidence of supernovae. There are isotopes, particularly iron-60, that have been identified in ice cores that are strong indicators of supernova explosions. So we think that our geological evidence on Earth supports this picture, that this local bubble was produced by 15 supernovae over the course of the past 15 million years. Our sun moved into it only about 5 million years ago. And as the final sort of exciting discovery, a lot of the local molecular clouds, so Taurus, Corona Australis, Ophiuchus, Pine Lupus, Chameleon, fall on the edge of the local bubble. So a lot of this star formation that is happening near the sun, a lot of the new birth of stars is happening thanks to supernovae, or the death of old stars. So old stars are dying, producing the local bubble, which is then producing new stars around our sun. And it's fascinating to think about the timescales of this, because 5 million years ago is not that long ago. You know, the dinosaurs were around 60 million years ago. So this is much, much more recent than the dinosaurs. But our galaxy has kind of changed substantially in that time. So this tells us that supernovae may play a big role in forming new stars. A similar story may tell us how our sun formed. So our sun may have formed in the shell of one of these big bubbly structures produced by supernovae. And a lot of the elements that make up our solar system and Earth and us came from supernovae, old generations of stars that produce bubbles like this. So it raises the big question, can we map the whole galaxy and find other bubbles, other structures like this throughout the Milky Way? So to summarize section 3, before summarizing all of the talk, we can study star formation using simulations, and especially the 3 major components: gravity, turbulence, and magnetic fields. 3D dust mapping allows us to compare real observations now with simulations, which is remarkable. That's something that wasn't possible even 5 years ago. And our sun resides in a local bubble, which we think was produced by 15 supernovae over the past 15 million years. These are the biggest explosions that we know of, occurring in a timescale much shorter than even things like the dinosaurs, which is quite remarkable. And our geological evidence on Earth supports this theory. And then finally, most star formation near our sun, so most of these new baby stars are being born thanks to some of those other bubbles. So thanks to the death of old stars. It's really the circle of life, but on galactic scales. So the only thing that's left next is new discoveries. So to take away from this talk, I hope that you've learned that we can begin to map our galaxy in 3D using dust and stars, which is a remarkable achievement in the field of astronomy. It's thanks to a lot of incredible scientists who worked on Gaia and these 3D dust maps all across the world. And 3D maps tell us about the locations and physics of molecular clouds. We can use these maps to learn about star formation and stellar feedback, especially supernovae. Then if we combine all of them together, we can actually make a 3D atlas for our local solar neighborhood and start to understand why we are where we are and what may have produced our sun in the long run. So with that, thank you very much for coming to the talk and for your attention, and be happy to take any questions.
Excellent. And thanks so much, Michael. This is super, super cool. We do have one question from Yulia on YouTube asking if the element isotope that you mentioned is the evidence of supernovas in Earth's geology, is this produced only during the supernova explosions, or does it come from anywhere else?
So that's a great question. My understanding, and I'll preface this by saying I'm not a geologist, so there is possible other production mechanisms then I'm not aware of, then that could be a possibility. But my understanding of the literature is that this isotope, iron-60, is predominantly produced in supernovae, if not solely produced in supernovae. So the discovery of iron-60 in the ice cores really suggests that it came from a supernova.
I guess kind of going off of that, do you think like that this local bubble is still expanding and changing shape? I know we're talking about like mega year time scales here, but just showing what you've shown so far about how it's expanded.
Yeah, no, great question. We think it still is, but only slightly. We think it's starting to reach the edge of its possible expansion, because it's starting to run into those two long straight things, and it's starting to run out of oomph, basically, for lack of a better word. We don't see it having a whole lot of energy to keep expanding. So we think pretty soon it's going to dissolve into the interstellar medium. We won't be able to maybe tell there was a bubble there in a couple million years. And then a new bubble will probably arise and take its place from new generations of supernovae.
Interesting. Another question for you, Duke, asking you to repeat the name of the app where you can look at the stars and the molecular clouds in 3D.
Oh, absolutely. Yeah, it's so our plot uses an app called CoSpaces. I'll put a link in the handout. It'll take you directly to the app you have to download, and then you can scan a QR code that I will also include in the handout to load the plot in the app. Yeah, and then you can walk around it in your apartment if you want.
Are there any additional questions? All right. Well, thank you so much, Michael. That was an awesome talk. I definitely learned a ton about stars and molecular clouds and everything in between. So thanks for taking the time to share your work with us. And thank you to everybody for coming tonight.
Yeah. Thanks, everyone. Thanks, Jacqueline.